and replied by another question to Leibniz, what if the order will be half? So Leibniz in a letter in September 30, 1695, and this is the exact birthday of fractional calculus, same as in this similar as classical calculus, replied, it will lead to a paradox from which one day useful consequence will be drawn. So 300 years old subject, but this development in this field is poor because of its mathematical difficulty. Right? But in last few decades, some researchers from various parts of the country, they have got some interesting results using fractional calculus. So day by day, this subject, or rather fractional derivative, is using increasingly in almost all areas of science and engineering. So these are the topics to be covered here. Introduction, fractional derivatives, fractional order system. So what is a fractional order systems? Its importance and different types of fractional derivatives, their applications, salient features of fractional order controllers, optimal control of fractional order systems. So here I'll be mainly talking about this application of fractional derivatives in control, and more specifically in the area of optimal control of fractional order systems, and then conclusions. Okay, so what is fractional derivative? This fractional derivative means derivatives of arbitrary real order. Say 0.3 order derivative, 0.4 order derivative, 1.5 order derivative, and so on. So this fractional order derivative is a generalization of integer order derivative. This can be seen that if the order of the derivatives are replaced by integer or numbers, then this fractional derivatives will recover integer derivatives. So this is more general, and this integer derivatives are the particular cases of fractional derivatives. Several definitions of fractional derivatives exist. Here I have given these derivatives, those I'll be using in this presentation. Riemann-Leibniz fractional derivative, Caputo fractional derivative, Grunwald-Letnikov definition, variable order fractional derivative, conformable fractional derivative. In addition to this, we have Ries derivative, Ries-Caputo derivative, Caputo-Fabrizio derivatives, and so on. Those I am not using here. Okay, so here is the definition of fractional derivative. Left and right Riemann-Leibniz fractional derivative of a function ft, and the function is defined in some interval ab. So this dA to t alpha is the fractional derivative operator. Okay. So fractional derivative of f of order alpha at t, left derivative, is defined this way. 1 by this is gamma n minus alpha ddt to the power n integration into t minus alpha tau n minus alpha minus 1 f tau t tau. Here this n is the smallest integer greater than alpha. Okay. And this is the right derivative of the function in the sense of Riemann-Leibniz. Okay. Now let us go through this unification of integer derivatives and integrals. So how this fractional RL derivative came directly from this integer derivative. So first fold integration of a function ft, this is defined a to t f tau d tau. This is very common, first fold integration. And then second fold integration of the function ft is a to t d tau 1, a to tau 1 f tau d tau. And in a compact form, this can be written into this way. So this is second fold integration. In a recursive way, we can have this third fold integration as this. So this is how, if it is continued, then finally we can have n-fold integration of a function f, where gamma function is defined here, 0 to infinity this. Right? So we have this n-fold integration. Now this n, if replaced by any real number or any fraction, we can have fractional order integration. So we have n-fold integration where n is integer number. Now this n will be replaced by non-integer number. Okay, so this is what is a fractional integration. Here minus alpha is used to denote this integration. Okay, so this fractional order integration of alpha of a function ft is this. Okay, the same thing, only the change is what n is replaced by alpha, right? So here to find, here is an example, to find a 0.3 order RL derivative, Riemann Leibniz derivative, short form of Riemann Leibniz is RL. So to find 0.3 order derivative, what we do, first we find 0.7 order integration, right? So 0.7 order integration, and then it is followed by first order derivative. So this is 0.7 order integration, alpha is replaced by 0.7. So this 0.7 order integration we have. Now we take first derivative of it, then this gives 0.3 order derivative. So the 0.3 order derivative 0 to t d 0.3 ft is first order integration, first order derivative of this 0.7 order integration. So finally we get this one. So this is the general definition of alpha order derivative in the sense of RL. Now next is the Caputo fractional derivative. Okay, so this derivative of a function ft, this is Caputo fractional derivative operator. C is used to indicate this is in the sense of Caputo. Right? So here is the difference. So this in our previously, first we do the integration, then the differentiation. Now here what it does, first we take the derivative of the function, integer derivative of the function rather, and then fractional integration. So this is what left and right Caputo derivative of a function ft, and this t is defined in some interval ab, and n is the smallest integer greater than alpha. Here this can be noted that this n minus 1, alpha is greater or equal to n minus 1. This equality symbol is given to indicate that if n is equal to 1, then it becomes 0. Okay, so at 0 order derivative means the function itself. Okay, so equality symbol is for that. Okay. Now how this Caputo derivative is computed? So fractional integration already we have defined. So this is the fractional integration. Okay, the generalization of integer order integration is the fractional integration. Now here to find 0.3 order Caputo derivative, what we do, first we take integer derivative of order 1, okay? Then it is followed by 0.7 order integration. So this is what 0.3 order Caputo derivative of a function ft. Okay. So this is equal to 0.7 order integration of dft, integer derivative, and this is equal to 1 by gamma 0.7 integration this thing. Okay. So in general, this is the general definition of this Caputo derivative of order alpha. Okay. Now here is Kuhnwald-Letnikov fractional derivative, left and right Kuhnwald-Letnikov derivative. So this is what this fractional derivative in terms of limit. Okay, so the function is defined as before within some interval a to b, right? So nh is equal to t minus a, where a is the starting point of the function and t where the function is executed. N is the number of nodes and h is the grid size. So this is limit h tends to 0, h to the power minus alpha, summation this WR alpha. This WR alpha is a binomial coefficient. So this WR alpha, this can be viewed in this way. This is basically NCR. This is basically NCR, where n and r are the integer numbers. Okay? So here, as this alpha is a fraction, so this is computed instead of factorials. This is computed using gamma function. Okay. So here, how this recursive way is shown, WR alpha is equal to this recursive way it is computed, where this W0 alpha is equal to 1. Okay. So this is what the first derivative of this function in terms of limit h tends to 0 ft minus h by h. Then second derivative of the function, third derivative of the function. So this is how, if it is continued, then we will have nth derivative of the function is this. Nr is the binomial coefficient, h is the step size. So simply here, this n is replaced by alpha. So we'll have the Grunwald-Letnikov fractional derivative of order alpha, and this is the derivative in terms of limits. Okay. So this is how this Grunwald-Letnikov derivative of a function, or fractional derivative of a function, is executed in terms of limits. Okay. So we have so many definitions: Grunwald-Letnikov, Riemann-Lively, Caputo derivative. Actually, what we do to compute this fractional derivative, if it is defined in terms of RL stands for Riemann-Lively. What we do, we use Grunwald-Letnikov fractional derivative. So for numerical purpose, we use Grunwald-Letnikov fractional derivative, and this is basically same as RL derivative. But for analytical purposes, for mathematical analysis and etc., we use RL derivative. And some cases, almost, for engineering applications, mainly we use Caputo fractional derivatives for mathematical analysis part, because it offers some advantages. But these two derivatives, RL and Caputo, they are not same in general. So here is the definition between these two derivatives. This is RL derivative, this is Caputo derivative, and this is the relation between these two. So if this alpha is in between 0 and 1, and then if ya is 0, then these two derivatives are same. Caputo and Riemann-Lively fractional derivatives are same, but in general they are not same. Okay. For other alpha values, the scenario is not so simple. Okay. So here is what this integer derivative versus fractional derivative. Integer derivative of a constant is 0, and derivative of a constant is non-zero in the sense of RL, but it is 0 in the sense of Caputo. So here is the difference. This difference, as it can be seen, this Caputo derivative, first we do in the derivative and then it is integration, and in the RL sense, first integration, then it is followed by derivative. So it makes the difference, and because of this, it can be seen that derivative of a constant is non-zero in the sense of RL, but it is 0 in the sense of Caputo. So for solving differential equations, natural initial conditions needed for integer order system. But for RL derivative problems, if the dynamics is described in terms of RL derivative, then these are the initial conditions needed to solve the fractional dynamic system. So these initial conditions are fractional initial conditions. These are not natural initial conditions. But in the sense of Caputo, these conditions are natural conditions, and this is same as integer order systems. So because of this, we engineers take the advantage of this Caputo fractional derivative, because it allows natural initial conditions. So this is what integer derivative is a point property. So it's just like to finding the first derivative, it is limit h tends to 0 fx minus h by h. So it is a point property, but this fractional derivative is a memory type operation. So let me go back. So here to find this alpha order derivative of a function at time t, what is needed? All previous values. So this entire history of this function is needed to know the present behavior of the system. So this is what some sort of memory type operation, but this is not a point property. In integer systems or integer derivative is what? The right derivative is negative of the left derivative. But here for fractional order derivative, the right derivative and the left derivative, they are completely different. There is no straightforward relation between left and right derivatives. So this fractional derivative is a generalization of integer derivative, and it finds its application almost all areas of science and engineering. So here is another derivative, variable order fractional derivative. So this is in the sense of RL. So here it can be seen that this order of the derivative alpha, this is not constant. It is a function of time. Here it is shown, but in general, this could be a function of time or any other parameter. So this is what is a variable order left derivative of a function ft and the right derivative of a function ft. A is the starting point of the function. Okay, so it is same as RL derivative, except that this alpha is a function of some parameter type here. Okay, now this is what is called type 1 representation of variable order derivative. In type 2 representation, what it does, uh, since this part is now a function of time, this is taken after this integral. So this gives a type 2 form of representation, and in type 3 representation, this is taken inside the integral, right? So they are completely different. Now here in this presentation, I will be using this type 1 representation. I am not going to discuss this type 2 and type 3 representation of variable order fractional derivatives. Okay. So here the variable order derivative in the sense of Caputo left and right, Caputo variable order fractional derivative. Okay. So first this derivative, integer derivative, then it is followed by integration. So here is the Kunwal-Letnikov definition of variable order derivative. It is very similar to fixed order derivative, but this alpha, the only change is alpha here is a function of time. And this is what a conformable fractional derivative is, very new definition, and the definition is very similar to integer order derivative. Okay, so this is what d0 alpha d0 dt0 to alpha xt. So this is what the conformable derivative operator. So conformable derivative of order alpha of a function xt is this x0 alpha t limit epsilon tends to 0. So this can be here if alpha is 1, then it becomes integer derivative, right? So if alpha is 1, then this part becomes 1. So it is t plus epsilon minus xt by epsilon. So it recovers conventional integer derivative, but this is not valid for alpha is equal to 0. Okay, And here is the conformable fractional integration. This IA alpha is the conformable integration operator. A to TF tau dA alpha tau. It can be noted that this integration is not the first fold integration of a function ft. This is different from first fold integration, and here is the relation. This d a alpha tau d tau, this basically means this a to t tau minus a alpha minus 1 f tau. Okay, so this integration, fractional order integration, this is not same as first fold integration. So a fractional order system is what? A system where the dynamics of the system contains at least one fractional derivative term. If we find at least one fractional derivative term, then this system will be called as a fractional order system. Most of the systems are fractional order. Almost all systems are fractional. So what we do for analysis purposes, we take the integer approximation of things. Okay. So for example, a capacitor, a pure capacitor is also a fractional order element. Its impedance is not 1 by SC. For a pure capacitor, its impedance is 1 by S to the power 0.999 into C. This is the capacitive impedance. So this is approximated as 1. Okay, so we write it 1 by SC. So here is a variable order system. So what is that variable order system? So the variable order system is what? Where the dynamics of the system will contain variable order derivative term. Okay. So here this is not a alpha. If the order of the derivative, this is not a fixed quantity, rather this will be a function of time or some other parameter. So here is the importance of fractional order systems. Representation is more realistic, and the real-time systems are fractional order. Okay, this is important. The representation is more realistic. Here, let us take an example of charging and discharging profile of a capacitor. Okay, so this is the charging profile. This is the discharge. So this is charging and this is discharging. So for integer system, what we do to know the discharge profile, the initial condition is at this point is enough to know the discharge profile of this capacitor. But if the system is fractional order, this initial condition is not sufficient. It needs all previous values, that is the charging profile of the capacitor. So in addition to this initial condition at this point, it needs the entire charging history or the complete history of the function to determine its discharge behavior. So the behavior of this system is much more realistic when it is represented by fractional order dynamics. And real-time systems are fractional order. Here is an illustration. So let us consider this example, stress-strain relationship of solids. So the stress is linearly proportional to strain. Right? For Newtonian fluids, it is the first derivative of this strain. This is the first derivative of this. And for intermediate materials, it is expected that this relationship will be somewhat in between. So this is what? Zero derivative of epsilon, and this is first derivative of epsilon. So for intermediate materials, solid and fluids, so it is expected that this order will be in between 0 and 1. This will be in between 0 and 1. Okay. So for intermediate materials, this is the stress-strain relationship. K is some constant, alpha order derivative, where alpha is in between 0 and 1. Now, when this is subjected to some parameter variation, this system, intermediate materials, and they are subjected to some parameter variations, maybe it is changing from solid to liquid or liquid to gas, etc. Then what happens? This dynamics no longer remain constant. That is, the order of the derivative, it does not remain constant. Rather, this order alpha will change with time or some other parameters. So here it is shown when it is subjected to parametric variations, then this is how the stress and strain changes. But alpha is the order of the derivative is a function of t and tau. T is time and tau is some another parameter is which is subjected to some parametric variations. Here is an example: infinite RC line. So if this impedance is calculated or it is viewed from here, the equivalent impedance, this will be said as ZB under root of this. When this ZA is R and ZB is 1 by, so this ZB, it is wrongly written, it should be a capacitor, pure capacitor. So then also the impedance, the overall impedance between these two is what? S to the power root over R by C, S to the power minus half. So it gives a fractional order behavior. Okay. So here is a fractance. This fractance is very similar to two-terminal capacitor. Sometimes this is called constant phase element, and this is developed at IIT Kharagpur. Okay. And it shows this impedance of this fractance is Q by S to the power alpha. So for pure capacitor, it is what? Q by S to the power 1. So for pure capacitor, alpha is equal to 1. But for a fractance, it is Q by S to the power alpha. Okay. And it shows a constant phase behavior for a particular range of frequencies. Okay. And this alpha here is in between 0 and 1. Okay. So here is another example: flow through wire. Now, if the dimension of the flow channel, suppose this is the flow channel, its dimension, height, etc., and width, all these are given. Rectangular flow channel, if this is given, we can find the volume flow rate, right? Let us consider a different situation. The volume flow rate is given, right? The volume flow rate is given. Then what should be the flow profile in some, this optimal flow profile? So some fluid is flowing. So this is side view. Okay. So H is the height, and here, so this is what the front view, and this is the flow channel or flow profile. So x is taken as a function of y. So this is quite unusual, but for here in this case, we use x as dependent axis. Okay, x is a function of fy, y is height of this flow channel. So it can be seen that this QH is the volume flow rate, C is a constant. So this volume flow rate is given by this integration, and this volume flow rate and the flow profile FH, they are related by a fractional manner. So if the volume flow rate is given, now to design an optimal flow profile, so there is no other option other than fractional calculus. Now this is what is an example of spring mass viscodamper system. Okay. So here for integer order system, so this will be a pure damper, so alpha will be 1. But here this viscodamper, it offers a force of, this offers the property of viscosity as well as elasticity. Okay. And this is how the dynamics is given. Okay. M is mass, B is the coefficient, damping, viscous damping coefficient, A is the spring constant, F is the force. Okay. And this viscodamping, one specific application of viscodamping is it is used in ships for damping mechanism. So this behavior, this behavior is a fractional order behavior. This is a fractional order system. Now, let us talk about this application of fractional derivatives in control. Okay? So here, this is what is a basic feedback control loop. Okay? RS is the reference input, E is the error signal, CS is the controller transfer function, and GS is the plan transfer function, CS is the controller. A very common controller is a PID controller. But here, a fractional order PID controller, this is how it is written. This transfer function of a fractional order PID controller. Okay, so it should be actually CS by ES. Okay, so here, in addition to this proportional gain, derivative gain, integral gain, we have another two parameters: order of the derivative alpha, order of integration beta. Okay, so it can be viewed in this way. This Kp, Ki, Kd can be used as coarse and alpha beta as fine tuning parameters. Okay, so it gives a better performance, a better control of the system. But the difficulty is what? In fact, the designing of PID controller or designing optimal design of Kp, Kd, Ki values, this is itself a difficult problem. And then how to design, in addition to this alpha and beta, how to tune this controller and how to realize this fractional order control. So these are the challenges. So this is what are the salient features of fractional order controller. So fractional order Pi alpha d beta controller, we have two additional parameters, better control, but the difficulty is tuning of this controller. Fractional order lead lag compensator, it gives what? Exact amount phase and gain compensation. So if I talk about the transfer function of this transfer function, say 1 by s, so this is what in gain form, this will be minus 20 log omega. Okay, so here from what we can get a gain of 20 log omega, right? So if it is s square, then 40 log omega, s cube 60 log omega, and so on. So integer multiple of 20. Now let us consider a situation, and in many power electronic circuits, okay, it is seen that say minus 12 dB, minus 16 dB gain is needed, right? So what we do, instead of 1 by s, if I use 1 by s to the power alpha, then it becomes 20 alpha. By selecting the values of alpha, the exact amount of gain and phase compensation is possible. Okay, so this fractional order lead lag compensator is capable to provide exact amount of gain and phase compensation. So in fractional order optimal controller, we'll see shortly that the control energy requirement is less. So these are some important features of fractional order controllers. Okay. So in this talk, I'll be mainly discussing on optimal control of fractional order system. So let me talk about this optimal control of integer order system first. So this is what optimal control is, a state space based approach. Okay. So nth order system, this nth order or nth order differential equation is converted to n linearly independent first order dynamics. This n state constituting state space of dimension n. So this optimal control or constraint dynamic optimal control, this is how it is defined. This is the state dynamics, dxdt fxut, state dynamics. This is the output equation, and the performance index or the objective function to be extremized is this. J is equal to this thing. Okay. This S is called the terminal cost function, okay, and this is called the integral cost function. Okay. So this J is general, which includes terminal cost as well as integral cost function. Okay. So the problem is what? The optimal control is to find the control u which minimizes this objective function J subject to the dynamic constraint dx/dt is equal to this. So this is the state dynamics with some given initial condition. So some objective function, minimize this objective function subjected to state dynamics xt0 is equal to x0. Okay. So here we have this initial time t0 and tf is the final time. Now depending on the time and states, final state, this problem can be viewed as a fixed endpoint or free endpoint problem, finite horizon or infinite horizon problem. That is this tf, this could be infinite also. Okay. And when it is finite, then it is a finite time problem. Tf tends to infinity, then it becomes infinite time problem. So what methodology is used to solve this optimal control of integer order systems? So there are two ways it is done. This is open loop control mechanism and the closed loop control mechanism. In open loop control, what we do, we define some Hamiltonian function h. This is equal to v plus lambda transpose f. So v is here, so this is v, this is v, and f is this. This is f. Okay. And lambda is called Lagrange multiplier vector. Okay. So these are the optimal conditions. Okay. So after using variational approach, calculus of variations, etc., integration by parts, we'll have this necessary conditions. So these are the necessary conditions. This is what is the control equation del h del u is equal to 0. H is Hamiltonian. This is del h del x is minus, this should be lambda dot. Okay. Minus lambda dot. Okay. Co-state equation, and del h del u is equal to x dot state equation. Now sometimes this lambda is called co-state because of the similarity of this state equation. So x dot is equal to del h del lambda, lambda dot is equal to minus del h del x. So because of this similarity, this lambda is sometimes called a co-state vector. X is state vector and lambda is called co-state vector. Okay. So these basic equations yield different conditions for fixed and free end cases, right? So in addition to this, I have not shown here, we'll have a general transversality condition depending on the final time and states. Okay. Now here, this similar problem is solved using, how this problem is solved using closed loop feedback control methodology. Okay. So this is what the objective function we prefer, a quadratic performance index. This is terminal cost function, same as before, S, and V is what? V is in this form. So this is very similar to S. This is S, terminal cost function, and this is what? This is V. Okay. So this is this X transpose QX. This is quadratic U transpose RU. So this X transpose QX, this indicates this, if this J minimization of J, this minimization of J, it means that minimization of this state components and this minimization of this control. Okay, that is the control to transfer the states should be not too large, right? So actually what happens to minimize this state component, what is needed? Large control energy. So minimization of this first integral term, it needs large control energy, while minimization of this U transpose RU, it needs small control energy, right? But we are minimizing this J. So, these two are conflicting in nature. So what it does, we use a convex combination of these two. Okay, and this the terminal part. It indicates that the final state this should be as close as possible to the origin. Okay, so here is the optimal control. U is equal to minus R inverse P transpose P. Okay, and it should be mentioned here that Q is a symmetric positive semi-definite matrix and R will be a positive definite matrix. The reason is quite obvious from here, because otherwise this control law will not exist, because we need R inverse terms here. Okay, so R must be positive definite. Okay, and uh, this is how this closed loop control U is equal to minus R inverse B transpose Px is obtained, because R is known, B is known, and P is what? P is the Riccati coefficient matrix, and for finite time problem, PTF is equal to FTF, where FTF is known. FTF is known from here. Okay, and we solve matrix differential Riccati equation. Matrix differential Riccati equation, which is solved backward in time, because that our integration time is what? The T0 to Tf, but the condition is given at T is equal to Tf. So it needs backward integration. So the solution of this matrix differential Riccati equation is difficult. Okay. Now, when this Tf is infinite, so this is what? It becomes infinite time or regulator problem. Then this part becomes derivative part becomes zero. So it reduces to algebraic Riccati equation. So the control equation that remains same, that U is equal to minus R inverse B transpose Px. This is minus R inverse B transpose Px. Okay. So for finite time problem, P is solved from matrix differential equation. Infinite time problem, it is the solution of algebraic Riccati equation. Okay. So now this is what is a optimal control of fractional order system. So uh, here is the difficulty that this no closed loop Riccati type solution is available. So we try with open loop solution. So here, as integer order system, we have open loop solution methodology and closed loop solution technique, or feedback control is possible for open loops integer systems, but for fractional dynamic systems, this closed loop control is difficult, and perhaps this is not possible. Okay, so we go ahead with open loop solution. So this is an important work, and this work is done by Agarwal in 2004. So this is the very basic work in the area of fractional optimal control. Okay, and more specifically constrained optimal control. Okay, so here is the objective function. J is to be minimized. All these are scalar. X is a scalar quantity. Okay, U is a scalar control input, and the state dynamics of the dynamic constant is given by alpha order derivative in the sense of Riemann Liouville. Okay, so for integer order system, what will be, this will be this alpha will be 1. Okay, so here is the difference. Okay, objective function it remains same as integer system, but the dynamic constant is different. So it can be viewed in this way: an optimal control of a fractional order system, or fractional optimal control, is what? When if the dynamic constant or the performance index or both contain at least one fractional derivative term, then this problem will be called fractional optimal control problem. So here we consider integer order performance index, okay, but the dynamic constant is given by fractional differential equation, and alpha is taken in between 0 and 1. Okay, so uh, doing this variational approach, uh, 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 integration by parts, okay, then finally these optimal conditions are obtained. Okay. So this is what T0 alpha alpha x equal to x plus bu. Okay. And alpha derivative of lambda, lambda is called co-state variable here, since lambda is a scalar quantity. So here it is variable, co-state variable. This is equal to qx minus ln, and this is the control equation. Now it is interesting to see that we started this problem with left derivative, because this is left derivative, left Riemann Liouville fractional derivative. But here, in addition to this left derivative, we have this right derivative. Okay, this d to 1 alpha lambda, this is what is the right derivative problem. Okay, so co-state equation is given in terms of right derivative. Okay, but if we write equivalent integer order equations, then this will be what? X dot is equal to ax plus bu, and lambda dot this is equal to minus qx minus a lambda Okay. Now if this alpha is replaced by 1, so this derivative, right derivative, this will be minus d lambda dt. Okay, minus d lambda dt. Okay. So this minus d lambda dt is equal to qx plus a. So it recovers integer order conditions when alpha is replaced by integer number. So this formulation is more general. Okay. And this integer order formulation, or integer order problem rather, is a particular case of this fractional order system. Okay, so here we have left derivative problem and right derivative problem. As mentioned before, that this left and right derivative, they are not same. For integer system, left derivative is simply negative of the right derivative. Okay. So we do not find any difference as such there. But here, as they are different, completely different, and there is no straightforward relation between left and right fractional derivatives, so the solution of this problem is difficult. Or the optimal solution of this problem is difficult. Okay. So these are the conditions: x0 is equal to x0 and lambda 1 is equal to. This is basically what the transversality condition. Okay. So here, no closed form solution is available for feedback control. So what it does, it uses open loop solution methodology to find state and control. Okay. So what is the development in the area of fractional optimal control till now? Fractional order Euler-Lagrange equation. This is the very basic problem, and this is what this extremization of this equivalent integer order problem will be. This term will be replaced by x dot. This will be replaced by x dot for equivalent integer problem. These are some xa is equal to xa and xb. These are the boundary conditions. Alpha is chosen between 0 and 1, and this is what the Euler-Lagrange equation, or fractional order Euler-Lagrange equation. Okay, so if we go with integer system, then this will be replaced by 1. Alpha will be 1, so this becomes x dot, and the conventional Euler-Lagrange equation will be. So this conventional Euler-Lagrange equation, this will be what? This conventional Euler-Lagrange equation will be del v del x minus ddt of del v del x dot minus ddt of del v del x dot. This is equal to 0. ddt of del v del x dot, this will be 0. Okay. Now here it can be seen that this is what is right derivative, and this right derivative, when alpha is 1, this becomes minus ddt. And this is left derivative. When it is alpha is 1, this becomes x dot. Okay. So if alpha is replaced by 1, then this fractional order Euler-Lagrange equation will recover this conventional fractional integer order Euler-Lagrange equation. So development of fractional Euler-Lagrange equation, fractional optimal control, constant fractional optimal control for different endpoint conditions as mentioned before, depending on the nature of states and time. This can be a free endpoint problem, fixed endpoint problems, etc. And then fractional optimal control of multi-dimensional system. Here the state dynamics is replaced, I mean this represented by in terms of state space. Right? Then time optimal control, fractional optimal control using indirect approach. This is what many cases what is done, this S1 by S to the power alpha, this 1 by S to the power alpha, this term is replaced by integer order, equivalent integer order state space representation, and the problem is carried out with this modified system. So this is what an indirect approach. Okay. So these are the development till now in the area of fractional optimal control. Now here we talk about fixed endpoint fractional optimal control problem. Okay. So this objective function is a quadratic in quadratic form. X is state, U is the control input, and this is what is the state dynamics alpha order derivative, and this derivative is taken in the sense of Riemann-Leibniz. Okay? And alpha is chosen between 0 and 1. However, this alpha could be any number. Okay? But here for simplicity, alpha is chosen between 0 and 1, and this is the initial condition. And the Q is positive semi-definite and R is positive definite. R is greater or equal to 0 and Q is greater or equal to 0. Okay. And these are the necessary conditions of optimality. So this is what a control equation, this is state equation, and this is co-state equation. It is interesting to note that we started this problem with Riemann-Leibniz fractional derivative. Okay, after doing the integration by parts, because this is required while formulating this fractional optimal control problem, we need some fractional integration by parts, and this gives this Caputo derivative, right Caputo derivative problem. So even though we started with RL derivative, left derivative, this Caputo right derivative automatically arises in the problem formulation. Okay. So these are the necessary conditions and they are the boundary conditions. Okay. So with this necessary conditions and boundary conditions, this set of equations are solved, because basically the state and control are the solution of these two fractional differential equations, linear fractional differential equations with this given boundary conditions. So what it does to solve this state and co-state equation, state and co-state equation, this inter-time domain, the inter-time domain is divided into n subdomains of equal space or equal grid size, and then these fractional derivative terms are represented or replaced in terms of their node variables, right? So when this is done, then this state equation, it looks like this, and this is the co-state equation. Here this Caputo derivative problem, this Caputo derivative is first converted to RL derivative using the relation between Riemann-Leibniz and Caputo, because the Grunwald-Letnikov definition that the numerical method to find the fractional derivative, this is for RL derivative problem. So we convert this Caputo derivative to RL derivative, and then we use this limiting definition. So this is what H is the state size, M is the number of nodes, okay, N is the number of nodes, okay. This is binomial coefficient W, and this X, M, and lambda, and these are the node variables. Okay. So this forms the 2n number of linear equations, and they are solved using available numerical methods for solving. So here is a numerical example. So this is the objective function, okay, and this is the dynamic constant. The scalar system is considered here, and these are the boundary conditions: x01, x1 is equal to 0. Okay. So using the method as discussed to this solution, this state and co-state variables are state and control variables are obtained here. Okay. So here this alpha is chosen between 0 and 1, and the solution is shown for different values of alpha in between 0 and 1. Okay, so grid size was taken n is equal to this number of nodes, this is taken 100. Okay, and these are the solutions shown for different alpha. So this is what, this is for alpha is equal to 0.77, this is alpha is equal to 0.87, this is alpha is equal to 0.93, this is 0.97, and this is 1. So from here it is clear that as the alpha value approaches to 1, the solutions are also approaches to 1, or okay, as expected. Okay. And here is another problem. This is what free endpoint problem. Okay. So here the final time is considered as free, but the state is fixed. Okay. So this is what the state dynamics fractional derivative is taken in terms of Riemann liability. This is the objective function, and these are the boundary conditions. And the final time, this TF is free. So an example of this problem is real-time example, aircraft landing. So when aircraft lands, or this touches active runway, so it has to touch at a particular point, or at a particular line of this active runway. Otherwise, what happens? This may hit this airport boundary. So here, the final time, it hardly matters if some more time is needed, or some if it lands before the actual time. It does not matter, or it hardly matters. But what matters is the final state. Okay, so the final state is fixed. Otherwise, there will be a problem. So this is a practical example of free final time problem. So here the final time is free, but the state is fixed. So these are the conditions. So these conditions are obtained how? This using increment of the first what it does, this use Hamiltonian, then take Lagrange multiplier, then use increment of the functional, then the first variation of the functional we extract and set it to 0. Okay. Then finally from there these conditions are obtained. This is control equation, state equation, and this is co-state equation. And this is interesting. This is the transversality condition, and this transversality condition allows to find the final time. Okay. And these are the boundary conditions given. Okay. So here solve this state and co-state as we don't know this this final time. So what it does, some shooting method type numerical method technique is used to solve state and co-state equation, right? So some final time is chosen, state co-state equations are solved using these conditions, and it is and we check this transversality condition whether this is 0, and the method is continued using some error criteria. Okay, so when it enters within the specified error limit, that solution may be considered as a solution of the problem. Okay, so here is an example of free final state problem. This is the objective function, state dynamics. Okay, x is the state variable, is the control. These are the boundary conditions. TF, the final time, TF is unknown, or this TF is free. Okay, so these are the state and the control variables. Okay, so again these results are shown for different values of alpha. So this is what 0.75, this is for 0.85, this is for 0.95, okay, and this for this for alpha is equal to 1. Okay, so it is it shows that the analytical result for alpha is equal to 1, this problem can be solved using analytical method. Okay, So this analytical result and the numerical result, they are same basically because they overlap. Okay? And this is what the control variable for different alpha. So here it can be seen that the time requirement for different values of alpha is different, right? So this is what for alpha is equal to 0.7. This is the time requirement. So if alpha value is increasing, the time requirement is more. Okay, so for more larger values of alpha, your TF will also be larger. Now here, one thing is interesting that for integer system, equivalent integer system, if these boundary conditions are interchanged, that is, if x0 is taken 1 and xtf is 10, then the final time it remains same. Okay, there is no change in final time for integer system, but for fractional dynamic system, if this boundary conditions are interchanged, then the final time requirement will be different. They are not same. And the reason is this, as mentioned, this fractional derivative, this is what is a memory type operation. Okay? So this is not a 2-point property. Now here is what this numerical method for solving fractional 2-point boundary value problem. As we have seen in last few slides, that this the necessary conditions it gives are the basically what this control state and co-state equation. So finally, it reduces to a problem of solving state and co-state variables, right? Where this one condition is at initial time and another is at final time. So it forms a 2-point boundary value problem. Okay, so 2-point boundary value problem. So these 2-point boundary value problems are solved new. Now, this if RL derivative is considered, then we find some Caputo derivative problem. Okay? Or if Caputo derivative, we will see that RL will automatically arise. Now, it was needed to find a general solution of 2-point boundary value problem, irrespective of whether it is a Caputo derivative problem or RL derivative problem. Okay, so here a general solution technique of 2-point boundary value problem of a fractional dynamic system is given. Although this is shown in terms of RL derivative problem, but this is equally applicable for Caputo derivative problem. This we will see later. Okay, and so this is what these are the state and co-state equations. Okay, so this is initial condition. This is the final condition. So 2-point boundary value problem. Okay. So this 2-point boundary value problem to solve, what it uses an operator. This operator is called a reflection operator. Okay, and this reflection operator, this is defined in this way: q lambda t is equal to lambda 1 minus t. So this is the definition of reflection operator. And this reflection operator, the beauty of this reflection operator is what? This converts right derivative to its left derivative problem. Okay? But please, it can be noted that they are not same. Right and left derivatives are not same, but it uses the advantage of converting right to left derivative. Okay, so here we use some sort of transformation: xt is equal to yt plus x0 to get 0 initial conditions, because we have seen in last few slides, because at 0 initial condition, the RL derivative and the Caputo derivative, they are basically same. Okay, so even though this is defined in terms of RL derivative, so this is quite equally applicable for Caputo derivative problem, because we have done this, or we are using this transformation. So finally, the state and co-state variables are written in terms of left derivative equations. Okay, so this left derivative is what? The state dynamics, and the right derivative, the co-state is given in terms of right derivative. So this co-state equation is now has been converted in terms of left derivative problem. So both state and post-state are now in terms of left derivative problems, and these are the modified conditions. Now this numerical method, as discussed before, can be used to solve this state and post-state equations. Okay. Uh, Here is an example of RL derivative problem. So this is the objective function, quadratic objective function. This dynamic constant initial condition, and the final state here is free. Okay, because the this final state free, it can be seen that this final state is free means this gives this transversality condition lambda 1 is equal to 0. So these are the results, okay, for state and control variables. Again, this result is shown for different values of alpha. Okay, so this is state and control, and this is what is the convergence analysis of the state and control. So alpha, a particular alpha value is chosen, and changing the node size, this problem is solved, and it is seen that the solution converge. So this is what is a Caputo derivative problem. The same quadratic performance index. The only change is what the C is defined in terms. I mean, this the derivative. Derivative is taken in sense of Caputo, and this is the initial condition, and these are the results. This can be noted that even though the problem is this objective function, state dynamics, they are almost same, except this this nature of derivative. Okay, so because of this change in derivative, these results are different. So these are the state and control variables for different alpha values of the derivative problem. Okay, so in last few slides we talked about this fractional optimal control of scalar systems with different endpoint conditions and a general solution technique. Now here this is what is optimal control of fractional order system, where the system dynamics is given in terms of state space. Okay, so fractional order state space is a very difficult problem. It leads to higher dimensional or sometimes infinite dimensional state space realization. Okay, so the reason behind this is the fractional derivative is derivatives do not follow this composition rule. So this is what p derivative and then q derivative of ft. This is not equal to p plus q derivative of ft in general. Okay, so this makes the difference with integer derivative. Okay, so and here is the difficulty. Okay, so here is the difficulty. So because of this, in a straightforward way, we cannot have state space relation of fractional dynamic system. Okay, so let me give an example. Let us consider if this dynamical system, and this or derivatives are integer multiple of 0.4, and this type of systems are called commensurate system. And if the selection of states are taken this way, x is equal to x1, 0.4 order derivative of x is x2, and so on, then finally this dynamical system is converted to state space form as this 0.4 order derivative. X is a vector, and these are the states. So this is equal to x plus bu. Okay, so this is the state space representation of this dynamical system. Now it can be noted that the highest order derivative is 2, but the fractional order state space, it leads to 5 states. So this dimension is high. So this leads to a higher dimensional problem. Okay. So what it does, so a general finite dimensional state space representation is shown here. Okay, so to take the advantage of Caputo derivative, this dynamics of the system is given in terms of Caputo derivative. Okay, so this is what the state dynamics of the system. Here u is the control input, no derivative of control is taken here. Okay, and these an, a2, etc., these are the coefficients. Xt is the state variable, bi is the order of the derivative, and they are fixed parameters. Okay, So the selection of states are what? This is very similar to integer order states. X is equal to x1, x dot is equal to x2. They are very similar to integer order states. Okay, so this makes the state space realization finite. Okay? And the selection of this variable beta I is equal to ri plus alpha I, and alpha is chosen in between 0 and 1. Okay? So this this dynamical system is now reduces to its state space form as Ex dot plus sum of this is equal to Ex plus Bu, where this E is a singular matrix. Okay, so this representation is finite and the states are very similar to integer order states, and it accepts this conventional integer order condition, initial conditions. So this E is identity matrix if highest derivative is integer or otherwise it is singular. Okay? This state space representation is finite, and the number of states, this is equal to m, and this m is in between what and this beta n is in between m and n minus 1. So here in this representation we have both integer as well as fractional derivatives. Okay, so this representation we call it pseudo state space representation, because this is not exactly state space, because this exactly state space representation, it means that we'll have only one derivative x dot is equal to ax plus bu, but here in addition to this integer derivative we'll have some fractional derivative, this term. Okay? And in addition to this, the state space means given the state dynamics x dot is equal to x plus bu, if we have the initial condition, we can predict the state at any point of time in state space. But here this initial condition is not sufficient. In addition to this, we need to provide this initialization function. Okay, so because of this we call it pseudo state space representation, right? Okay. So now here is one circuit, and in this circuit this C is what this is a pure capacitor, and CF is a fractional order capacitor. Okay, so doing circuit analysis and choosing this V1 and V2 as node variables, this the pseudo state space representation is given in this way. So this is same as we have mentioned before. So this is what E matrix, and this is P matrix. Okay. And this is the output equation. Okay. Now here it uses this pseudo state space representation to formulate fractional optimal control problem. So here J is what is the objective function, and this x is the state vector. So here x is n dimensional, and U is a scalar control input. So extremize this subject to this state dynamics. The states, I mean this constant is given in pseudo state space form, and these are the conditions, initial condition. Final state is chosen, we choose this is free, and there's a final time problem. Okay. These are the this E, A and Pi, these are n by n matrices. B is a vector of dimension n cross 1. Q is a positive semi-definite matrix, and R is positive. So these are the methods actually, or these are used to develop this necessary conditions. Okay, and finally the equating this coefficients of this delta x, delta u, delta and lambda delta u equating to 0. This state and co-state equations are obtained. So these are the state and co-state equation. So this is state equation, this is co-state equation, this is control equation, and this is what is the transversality condition, and this is the initial condition. Okay. Now to solve the state co-state, numerical method is used. Here one example is shown. So this is the objective function. Okay. So this objective function is in again quadratic form, subjected to this state dynamics, and these are the initial condition, and the final state is free. Okay. So this problem is solved, and these are the results shown here. This is state, and the state x1 is basically x. Again this result this x is shown for different values of alpha. Okay, and this alpha, this alpha here is equal to, or here this beta is shown. So this beta is in between 1 and 2. So we write this beta is equal to 1 plus alpha, and alpha is in between 0 and 1. So finally, for different values of beta, it is shown. X is x1, and this is state x2. This is x dot actually, and this is the control. So here from also it can be seen this is for beta is equal to 1. This is for beta is equal to 1, and this curve, this is for beta is equal to 2. So the control energy requirement for beta is equal to 1 is less, and as the beta value is increasing, it demands larger control, more control energy. Okay, so for fractional optimal control problem, what we observe, as the alpha value reduces, it demands small control energy. Okay, so in earlier slides, we talked about open loop solution of fractional optimal control problem. Okay, so here one closed form solution is presented. Okay, so here this is the plant dynamics, and the derivative is taken as a conformable fractional derivative, right? So this here is the definition already discussed, conformable fractional derivative, and the order of the derivative is taken between 0 and 1. This is the objective function, and this can be noted that this is not same as I mean this in earlier performance indices, and because this parameter, this operator d0 alpha is different, because this dA alpha, this is equal to tau minus A alpha minus 1 d tau. So this is not ordinary integration, rather this is what is integration of order alpha. Okay, so finally the optimal conditions are obtained using variational approaches. So these are the optimal conditions. This post-state equation, this is state equation, and this is the control equation. So here this is transversality condition, and Hamiltonian is defined in this way. Okay. So to solve this state and post-state equation, so finally the state and post-state equations are written in vector matrix form as this. So this is very similar to Z. Okay, so the Z elements are x and lambda. Okay, so this Z is a vector, and this conformable derivative of Z of order alpha is equal to Az. Please note that the 0 is the initial point where the function starts. Okay, so using this fractional integration operator, this equation is written in this way. So we use this fractional integration operator I0 alpha. This is equal to a integration I0 alpha zt. So finally it gives zt is equal to z0 plus this. So in a recursive manner, we get the solution of this set, that is the state and post-state variables. So finally this for n is equal to 0. So this is z1, and z2 is equal to this, and finally zn is equal to this. And when n tends to infinity, we get a closed form solution of this. So this is the closed form solution. Okay, so these z elements are already, I have mentioned, this is state and post-state. So here from we'll have the state and post-state, and z0 is what? This x0 and lambda 0. Okay, so here is a numerical example. This is objective function, state dynamics, initial condition, final state is P, and these are the state and post-state variables. I have not shown here their analytical expressions, only results are shown here. And for different values of alpha, these results are produced. Okay. Then a variable order 2-point boundary value problem. So we have, from this previous analysis, what we have seen, that this finally this formulation of fractional optimal control problem, it boils down to solution of a two-point boundary value problem, right? So here for variable order system, we have not shown the mathematical part here. So only uh, this, this state and co-state equations are written here. Okay, this is the state equation, this is co-state equation, and this state equation is what is given by uh, variable order Caputo derivative of left variable order Caputo derivative, and co-state equation is right variable order RL derivative. So these are the state and co-state equations, and these are the what the boundary conditions. So this two-point boundary value problem is solved using numerical method. Okay, so the numerical method is similar to that the dividing this entire domain, time domain, or discretizing this entire time domain, and then replacing uh, this fractional derivatives in terms of node variables. Okay? And then finally, these are the what the numerical approximations of this state and co-state equations. So for these values of these parameters, this state and co-state are shown. This is what this curve is alpha is equal to 1, and this is alpha is equal to 0.6 fixed order, and this intermediate curve, this is for alpha is equal to 1 minus 0.40. So this is chosen in this way to show that at t is equal to 0, this becomes what? 1, right? 1 means this result, and t is equal to 1, it is 0.6, means this value alpha is equal to 0.6. But it is interesting to note that when this alpha is a time function, so it does not remain within this two boundary, I mean these two curves. Okay, the reason being, as mentioned before, this fractional derivative is what is a memory type operation. So we cannot expect that the result of alpha is equal to 1 minus 0.4t, it must lie between these two results. It doesn't happen. The reason is memory type operation. Okay, so these are what the state and control inputs. So, and finally the conclusion. Okay, so this fractional calculus, it took 300 years to develop. Fractional order control is just 3 decades old, still at its infancy. So many more fundamental problems need to be solved before we can fully utilize its potential. Okay. So these are the references. Thank you. So if you have any question, please.
Any queries? If you are having any queries, please raise. Sir, I think no queries, sir.
Okay, thank you.
Thank you, sir. Thank you very much, sir, for very valuable and informative lecture. So I think so participants have gained some knowledge regarding optimal control problems and applications of fractional order derivatives. So once again, thank you very much, sir. On behalf of Rajkiya Engineering College, Electrical Engineering Department, Sonbad. Thank you, sir.
Okay, thank you so much. Bye.
Thank you, sir. So, dear participants, next session will start at 11:45. So, please join at least 5 minutes before starting of this session. Thank you.